This video is to supplement the Dating the Earth content page number 50. The slideshow or slide deck is available in the Unit 2.1 overview. Highly recommend you go through some of these slides. It's about how we got to understanding the age of the Earth, what people thought in the past. But I want to focus on radiometric dating, and I don't want the video to be too long, so go over these slides on your own. This is just background information. So before you understand radiometric dating, you have to understand a couple of terms. An isotope, what the half-life is, and then what we call parent isotope and daughter isotope. An isotope is a form of an element that has a different number of protons and neutrons. So let's think about carbon. We know what carbon is, and you've done the calculation before. You know it has 6 protons, and you can calculate it has 6 neutrons. Well, there's something called, this is carbon-12, the normal one. There's something called carbon-14, where it has a different number of protons and neutrons. I'm going to have 6 protons and 8 neutrons. Now, when some elements have different numbers of protons and neutrons, we call them isotopes. And in many cases, this is very unstable. And it actually makes the atom break down over time. We call these like radioactive. So an isotope can break down by itself over time. One example that we use a lot is uranium. Uranium is radioactive, and it'll break down over time into lead. It actually releases energy, breaks down, and will turn into lead over a certain amount of time. So it's an isotope, a radioactive isotope. So when we look at radiometric dating, we have 2 terms, parent isotope and daughter isotope. The parent isotope is the original radioactive isotope, for example, like uranium. That's the one that does the breaking down, radioactive breakdown. And what results from that, what's created, is called the daughter isotope. So parent isotopes break down and they create daughter isotopes. Now scientists have this term half-life, which is the amount of time it takes for a parent isotope to decay half of its mass in a daughter isotope. We're going to practice this later. There'll be more videos, but this is just the basics, all right? This actual radiometric dating, if you go into geology, can be a little bit more complicated than this, but we're just going to get the basics down so that if you go on to doing anything in geology or dating rocks or fossils, you'll have a great understanding of it and you can learn more based on what we do here. So let's say you find a rock in your backyard, right? Well, the way radioactive isotopes work is that they break down over time. If you find this rock, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 uraniums in it and no lead, then you know that this rock has to be pretty new, because uranium is a radioactive isotope. It'll break down over time. If it never broke down into lead, right, you have, out of the 12 atoms that are in this rock, 12 of them are uranium. That means you have 100% of the parent isotope. It hasn't broken down into the daughter isotope, so you know that no half-lives have gone by, and this is a brand new rock. Brand new rock. Probably was just solidified. You might live next to a volcano if you found that. Right? But let's look at what one half-life looks like. Let's say you found a rock that looks like this. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 molecules total, and 6 of them are lead and 6 are uranium. Now what you need to understand is that uranium breaks down into lead. So this rock at one time used to be like this, 100% uranium. But that uranium is unstable, so it breaks down radioactively and turns into lead. So if you find this rock in your backyard, you know that it's not new. It's had enough time for it to break down. Well, how much of it broke down? If you count it, right, 6 over 12, it's half. This rock now has 50% of its parent isotope left, 50% of its daughter isotope left. The original mass of this rock used to be 12. Now it's 6 of uranium. 12 uranium broke down to 6. Scientists call that one half-life. That's the definition of a half-life. Time it takes for it to break down its original parent isotope by half. As you break down the parent isotope, you create daughter isotopes. And they know the number. This is about 710 million years. That's how long that takes. So one half-life for uranium, 235 specifically, is 710 million years. All right. Now, what someone might think is that, all right, well, after another year, there's going to be 0% left, because there's from 150% is gone, another 50% will be gone. But no, actually, it works out like this, where 100% breaks down to 50%, but then after another half-life, 50% of what is here will break down into what is remaining. Meaning, if you have 6 uraniums left here, what's half of 6? 3. 3 will be left. So half-life always halves, or sorry, I should say radiometric, radioactive breakdown, or decay, always breaks down half of whatever mass is left. So if you start with 12 uraniums, that'll break down into 6 and create 6 leads. Then if half of that breaks down, half of that uranium, 6 will turn into 3, and it'll create more leads. Eventually, it'll just keep breaking down, and it actually never gets to 0 uranium. It just keeps halving and halving and halving forever. However, if you find a rock like this one, the cool thing is that you can calculate how much of the original parent isotope is left. And when you do that, you can figure out how many half-lives went by. So in this one, right, we know that it started with 100%. After one half-life, it had 50% left, one half-life, which we know is 710 million years. We know that after another half-life, 25% of the uranium is going to be left. That's 2 half-lives. That's another 710 million years. We can just add those. This rock would be like 1.42 billion years old. We're going to practice that. All right? But make sure you study these terms. What half-life is, isotope and parent isotope.